In the previous video, we talked about esterification of carboxylic acids, and I have the general reaction scheme here. So you start with a carboxylic acid, or Ca, as an abbreviation. We add an alcohol under acidic conditions, and through the mechanism, we form an ester functional group where the OH oxygen from the carboxylic acid is now bonded to the carbon chain from the alcohol. So that's represented by R prime. And then H2O is a byproduct. We lost water in the reaction from the main molecule. So let's do an example. We'll just predict the product. We'll start with beta methyl hexanoic acid. So a little bit of nomenclature review as well. Hexanoic acid means we have 6 carbons in our main chain. Our terminal carbon is a carboxylic acid carbon. So we have 1, 2, 3, 4, 5, 6 carbons total. The alpha carbon is the carbon bonded to the carboxylic acid carbon. So our beta carbon is 1 carbon to the left. So right there is where we put the methyl group on the beta carbon. Okay, so if we have beta methyl hexanoic acid and we add ethanol, CH3, CH2, OH, it is the solvent, so it's in large excess. And then we will add catalytic sulfuric acid. So enough for the reaction to occur, but this is a catalyst that's not actually involved in the reaction mechanism, and we've seen that in the previous video. Okay, so if we have beta methyl hexanoic acid and we're adding ethanol under acidic conditions, then our final product is going to be an ester. Everything except for the hydrogen from the original molecule stays the same. Now, through the mechanism, we see that this oxygen that I just drew there is not actually the oxygen from the original molecule. It's from the solvent, but it's in the same location, so it looks about the same. Still have the carbonyl, and then now instead of a hydrogen bonded to this oxygen, where we only have one single bond to it right now, instead of the hydrogen being there, the carbon chain from the solvent is now bonded to that. So this is our ester product. So if we trace atoms and follow the mechanism, so specific atoms that come from the carboxylic acid or the solvent, the CH3, CH2, and the oxygen from the solvent are what is bonded here. Then everything else, so carbonyl, that carbon, and the remaining carbon chain, are all of the other atoms present in this product. And then if you look back at the mechanism, you'll see exactly how that occurs. Now, this reaction can occur intramolecularly. So if we have a long carbon chain, carboxylic acid on one end, and an alcohol on the other end, that reaction could occur within one molecule. So here's an example. Okay, so here we have a molecule that has both a carboxylic acid on the right side of the molecule and an alcohol on the left side. So that OH group on the left side of the molecule that oxygen has non-bonding electrons. And so if we're under acidic conditions, we donate a proton to the carbonyl oxygen. That carbonyl carbon, the carboxylic acid carbon, is activated. It is susceptible to nucleophilic addition. And so this oxygen, I'm skipping steps in the mechanism, but just generally to show you, this oxygen can then bond to the carbonyl carbon. We break that pi bond. And actually we'll show in this abbreviated arrows, this OH group would leave. So we have these steps that I've shown here and proton transfer reaction. So this is not a complete mechanism. This mechanism would follow the same steps as the previous video. Only difference would be, instead of adding a new molecule, a new alcohol molecule, you are adding the alcohol from the left side of that chain to the carbonyl carbon. So this is not a complete mechanism, just to generally show you what occurs. This would produce, before we draw that, let's count our carbons. So carbonyl carbon will be carbon 1, 2, 3, and 4. And so in our product, we have our carbonyl carbon, that's carbon 1. Now carbon 2 is here. Carbon 2 is bonded to carbon 3. Carbon 3 is bonded to carbon 4. Carbon 4 is bonded to the oxygen, which is now also from this longer pink arrow bonded to carbon 1. We've kicked off the OH group through the mechanism. And so this is a cyclic ester. This is actually called a lactone. So there's our ester product for that intramolecular esterification reaction. Now, a little side note about lactones. These are often used, lactone and lactone derivatives. Are used as flavors and fragrances. So lactones have a fruity and dairy scent or flavor. Okay, one little bit more to talk about for this esterification reaction. Now we've started with a carboxylic acid and formed an ester. If you take an ester and put a new alcohol solvent or add a new alcohol solvent, the ester can go through what we call a transesterification process. So we won't do the mechanism, but we will show the reaction scheme. So in a transesterification reaction, we start with one ester. So ester 1 will add an alcohol, alcohol 1. These occur under basic conditions. And we'd form a new ester and a new alcohol. So let's do an example here. Here is the product of the reaction in our previous video. So when we went through the mechanism, we made methyl benzoate. So this is an ester. We have an OCH3 group in that molecule. Now if we add, let's add butanol, so we're adding butanol in the presence of the ester methyl benzoate. Under basic conditions, and that base should really indicate the basic version of the alcohol that's being added. So in this case, we could have potassium as a counter ion, and then this butoxide ion. And then the product, so ester 2 in this case, would be butyl benzoate. So the methyl part of our starting material leaves as the new alcohol, and the butanol alcohol starting material then is then added to the carbonyl. So we would have our carbonyl stays the same, and then now here we would have the butyl chain. So 4 carbons. So this is butyl benzoate. And then methanol as the second alcohol. So let's trace some atoms here. The carbonyl and the phenyl group are present in both esters. This OCH3 is now present in the second alcohol, so the alcohol product. And then this oxygen with the 4 carbon chain is now present in the second ester, so the product ester. Now this reaction, one ester, for the most part, isn't favored over the other. And so this reaction is driven forward by using excess butanol, in this case, so excess reagent, or distilling or removing the methanol product, so that second alcohol. So let's just write this down. One ester is not favored over the other. So one could drive the reaction forward by using excess butanol. So one of our reagents, one of our starting materials, and distilling or somehow removing methanol, one of the products. So this follows Le Chatelier's principle, which we've talked about in the past. If we have a reaction in equilibrium, we can drive it forward, in this case by adding more reagents or removing products.